Okay, so we talked about sequences, so now I want to talk about series, which is the main focus of this chapter. What is a sequence? Yeah, it's just a list, right? It's a list. There's the first number, there's the second number, there's the third number, there's the fourth number, right? So a series then okay, so in this sigma, we've seen that, we know what that is, we've seen that, that's sum, right? So we're summing up, starting with 1 to infinity, a sub n, right? So let n be 1, we get the first term of the sequence, a1. And then we get that a be 2, we get the second term of the sequence, a2, and then we're a3, a4, and now we're adding all those up. So what does this mean? It means take the first term of the sequence plus second term of the sequence plus third term, and then just keep going. Okay, so when you see this, what you think this. Because we're going to learn all these different rules, all these different formulas, and if it's this, you do this, and it's this. But you can't ever lose sight of when you're given a sum, you're given a series, like this sigma notation with this complicated expression, you still have to always keep in mind, think that, what is it? It's the sum of many terms.
You don't cap it half the ellipsis plus an.
Well, it just keeps going. I mean, so I could.
Like you could plus an minus 1 plus an.
What's that?
Like you could cap it with like plus an minus 1 plus an, right?
And be done? Like that? The problem is, I mean, that kind of gives it the feel that it's a finite sum, right?
So we just leave it with the ellipsis as.
I mean, it's not wrong. Do that.
Oh, that's conceptually confusing.
You brought it up.
Yep, I did.
Well, but see, n goes from 1 to infinity. So which n is it? So when you write it this way, this is a little confusing to me.
Yeah,
Which n are you talking about?
that's confusing. This would
Just put A.
Yeah, because yeah, it's just going on. N changes and starts at 1 and goes to infinity.
no, this said that.
Okay, so remember our an is 2 minus 1. So example. So if we had this, And what would that be? So, remember what the sequence was? 2n minus 1? What's the sequence? No, what is the sequence, though? What is the sequence 2n minus 1? Remember what you get when you do the sequence 2n minus 1?
Yeah. What do you ask?
What is the sequence? Do we know what sequences are? What is the sequence 2n minus 1?
Are you asking for
One, three,
What is the sequence?
1, 3, 5.
1, 3, 5, 7, 9, 11. Oh, you mean what is the sequence?
No, that's what you mean.
What?
Odds, right?
So yeah, it's odds starting with ones, right? So it's 1, 3, 5, 7. So then what would this be?
It's sum of all odds.
1 plus 3 plus 5 plus 7 plus 9. Okay, so when you add, so how many things are we adding together? So when you add an infinite number of things together, don't you just get infinity?
Yeah.
So I guess we're done with the chapter.
Nope. I'm done. Let's go home. Get on that.
Right? What's the point of this? If you add an infinite number of things together, it'll just be infinity.
It's the same thing with the curves and like kicking it off quickly enough to be able to like accrete enough quantity.
Okay. All right. Why? How could it converge if we're adding an infinite number of things together? What's that? It has a limit. What does it say?
The
It.
magnitude of the n terms want to be relatively minuscule in some cases.
Or we have to have like rules, right?
What's that?
Like if we have a rule that limits, to the amount that it goes, maybe then it could have an impact.
One case is if each term as the sequence, so as it continues on, it gets closer and closer to 0. So you add it up, and they get smaller and smaller and smaller, and you get a finite value.
Okay, so the only possible chance we would have for a series to converge to a finite number is what about the sequence? What would have to be true about the sequence?
House converge
Has to converge
Converges.
to 0.
to 0. Right? If it converges to 3, if the sequence converges to 3, you're getting closer and closer to 3, then what about the sum? What's happening in the sum? In the end, you're just going to be adding what? 3 plus 3 plus 3 plus 3. Going to converge? No, it's going to be infinite. So the only, and we talked about this before when we talked about improper integrals. So the only possible chance that a sum of an infinite number of terms could converge is if that sequence is, what's happening to that sequence?
You eventually add nothing.
Okay, so the sequence would then what?
Converge.
Converge to 0, right? Converge to 0. So, like for instance, 1 over 2 to the n. What sequence is that? What sequence is that? What sequence is it? 1 half, 1 fourth, 1 eighth.
It converges to 0.
Okay, so the sequence converges to 0. What about the series? So 1 half plus 1 fourth plus 1 eighth plus 1 16th.
But it reaches a finite, it goes to a certain limit.
Okay.
Finite number.
And what finite number does it go to?
Thinking 1.
I don't know what part of the series is.
1. Because first you have half a number, and then you're adding half that number.
Okay, so you're going to first add a half, and then
It's like a philosophical
Adding
point.
halves.
half of that.
And it's going to approach 1, so I'm going to have like twice that half.
I agree.
Yeah. Brandon's all over it.
That's a good, the way you said it, yeah.
Yeah, so you're always adding half of what you added before. So we start with a half, then we add another fourth. So we get 3 fourths, and we add an 8, we got 7 eighths, and we add a 16th, so we got 15 16ths. And so, will we ever get to 1? always, but we can get as close as we want to 1. So as long as you take enough terms out there, you can get as close as you want to 1. So therefore, if you were able to add up all infinitely numbered terms, it would be 1.
Yeah, that's nice.
There's some story or fable about what the rabbit that always, or the frog, or always jumps halfway to the wall, right? This is what this is like. Always jumping halfway to the wall. So you can jump half of the distance, and then a fourth, then an eighth, and a 16th. And then if the frog kept jumping for infinity, it would reach the wall. But as long as there's a finite number of terms, he's just a little bit short. But we can get as close. He'll eventually get there if you added all the terms together. And this sequence definitely converges to 0. And so that's the requirement. Okay? So if the sequence converges to 0, then the series converges, right? Let's put that question on hold, okay? So let's look at a type of series called a geometric series. Okay, so what I want you to do is I want you to write out what that series is. Okay? You see that? You think what? Write out what that series is. Okay? Write it out.
A and R constants.
A and R are, yes, A and R are constant values in the sum. Okay. A is like the coefficient, and R is your base. So you should be able to write out what is the meaning of that, or when you see that, what do you think? Okay. Okay, Tyler, how'd it go?
You want me to tell you what
Yeah, uh-huh.
AR to the 0 plus AR to the 1.
And what's AR to the 0?
Well, hey,
Tyler.
sorry.
Okay. Plus?
AR to the first
Okay.
plus AR to the second plus AR to the third.
This is what you should have. Did you get it? So the sequence is these terms, and then the series is adding them up, right? The series is adding them up. Okay, and then this is A is not equal to 0. If A is equal to 0, this is trivial, right? It's just 0. So, okay, so when does the geometric series converge? So, all right, will that be a matter of A or of R when the geometric series converges? Is that going to be dependent on A or dependent on R? R, okay? So if it converges, so A is just like a coefficient, it's just you just multiplying by some number. So what's going to matter is the value of R, okay? So let's do so we're gonna sum up the first n terms. Okay, sum up the first n terms, and we'll call that Sn. Okay, that's the first n term. Sum of first n terms.
Is this related to P to the N?
Oh yeah, a little bit. It does. So the sum of the first n terms would be our a plus ar plus ar squared, only up to n. And now what I'm going to do is I'm going to take that same expression and multiply by r. Why do I do that? Because it works. So I'm going to just take this expression of the sum of the first n terms. I'm going to multiply both sides by r. And so when I do that, I get the first term now will be ar. And then ar squared. And then the last one will be ar to the n plus 1. Yeah, go ahead.
Would it be A over R for the first term, and then plus?
No, I'm multiplying this sum times r. So it's like multiplying both sides of the equation by r to keep it equal. Does that make sense?
Yes.
Yeah. So I'm multiplying both sides by r. But then I'm gonna shift it over. I'm gonna move my terms over so that they match up with the one from before. So then we won't have the a term, but we will have this new term out here, ar n plus 1. Fair? So now I'm going to subtract. Why do you do that? Because it works.
To achieve what?
We're trying to figure out for what values of r this thing converges.
Okay.
And this is how you do it.
Sure.
Okay, so I'm going to subtract these. All right, so on the left, I'm going to get Sn minus r Sn. What will I get on the right? All these are going to go away, and I'll just have a minus that last one over there.
Okay, pulling that Sn off.
We are. So we're going to solve for Sn. And we're going to get, and I'm going to also, so that's dividing by 1 minus r. Do you see that? Factoring out Sn, left with 1 minus r, divide by 1 minus r. And so that equals a over 1 minus r minus I kind of blew this, sorry. So the sum of the first n terms is going to be, this is going to be n minus 1 here. Right? Because this is a1, a2, a3, so it's always, the exponent is 1 less than the term you're on, so that has to be n minus 1.
Okay.
And this should have been n. My fault, sorry. So this is just n.
So what is it?
What's that?
For the negative for the RSN, like the last term is AR to the end.
Because you're multiplying by, we multiply this whole thing by r, so every term gets multiplied by r. So if you have n minus 1 r's and one more r, then you have n r's. You asking about this right here? Yeah, that's this times r. Right? I'm multiplying every one of these by r to get the new sum. So if I multiply by one more r, then I have n r's multiplied together. Can I answer it? You still don't want?
Yeah, I don't understand.
Not really tracking it.
So did you understand? The sum of the first n terms starts at a and goes up to ar to the n minus 1. Is that okay?
Yeah.
So I'm just multiplying both sides of the equation by r. So everything gets multiplied by nr. So this is times r, then this is times r, then this is times r. Everything gets multiplied by r. So here's ar squared, ar cubed. So then the very last term will be this thing times r, which will not have n minus 1 r's anymore. That'll have n r's then. And then when I subtract, I get just this a and just this minus ar to the end. Okay, so I factor out Sn, divide by 1 minus r, and then I split it up into two fractions. And so now we're asking, when does this converge now? So when, for what values of r, will that sum converge to a finite value? So you have to look right here. For what values of r will this thing converge? So r would have to be, we need it to get smaller instead of blow up and explode. So what values of r for n make that thing get smaller rather than blow up? I keep multiplying r by itself over and over and over again, and I need that thing to get small.
Already talked about that thing between 1 and 0.
-1, right? Right here. So we need this to converge. So we're multiplying by r over and over and over again, and we need it to get small instead of diverge. So what values of r make that work?
Between 0 and 1.
All right, that's the idea. -1 and 1.
Yeah, so we did earlier.
What's that?
So we did earlier.
Yeah, yesterday.
Yeah, yes.
Yeah. So r has to be between -1 and 1, and then what happens to this? As n goes to infinity, when r is between -1 and 1,
Zero.
that goes to 0. So then the sum, so Sn goes to a over 1 minus r. Otherwise, divergent. So if r is something else besides in this range, then this thing diverges because that won't go to 0, right? We need that thing to go to 0 as n gets big. And when it does, then what we're left with is a over 1 minus r. So this is the condition for convergence. And this is what the sum equals. So go back to the one we did before. We did the sum of 1 over 2 to the n. So let's just do a variation on it so it matches this. So can I erase? Are we good here?
I'm still kind of confused about how the r being between -1 and 1 is going to make that expression a to the r n over 1 minus r go to 0.
Yeah, so if you just keep taking, say, point A is 0.8, you just keep multiplying by 0.8 forever. You keep taking 80%, 80%, and that's going to go to 0. So we did that yesterday.
I just say it one more time.
So haven't you ever in your calculator, you go times 0.8, and you go equals, 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 equals. You've done this, right? And you just keep multiplying by 0.8, and then what happens eventually? What does your screen show?
Smaller?
And your screen eventually shows 0.
Okay, so it'll turn to 0 on top.
That whole expression will go to 0 for large n.
Therefore,
When r is in this range. So if you have some fraction of 1 and you keep repeating multiplying by it, then that just gets as small as you want it to get, and the limit is 0. So then that whole thing goes away, and then so our sum is a over 1 minus r.
Because when R is negative, or oscillating, eventually it's just.
Yeah, so that's going to go even faster because you're add, subtract, add, subtract.
Oh.
So it's going to
Yeah.
it's going to
That's cool.
go to 0 even faster. Okay, so what about this example? So if we had n equals 1 to infinity. So this is basically, oh, let's do 2 to the n. So this is basically what the very first example we started with, right? 1/2 plus 1/4, right? So can we get that to look like, can we get that in the form of a geometric series? So what is our geometric series again? It's a r to the n minus 1. So can we get this to have this form right here? How could we do that? What's that? Okay, that's a good start. So we got n equals 1, 1/2 to the n. Is that the form? A r to the n minus 1?
What about 1 to the.
What we need is we've got 1/2 to the n. We need 1/2 to the n minus 1. So how can we get it to make it look like our geometric series?
Put like maybe an A out front, and then put n to the minus 1.
Okay, and so right, so there's some value of a that we need. So what the question is, what value of a would make these two things equal? Would make this sum equal to this one? So here I have what, n 1/2 multiplied together, and here I have n minus 1 1/2 multiplied together. So what value of a would get me to be equal to 1/2 to the n?
1 to the minus.
How many 1/2s are multiplied together here?
And
How many 1/2s are multiplied together here?
Also half.
So what do I need here?
N plus
It's not. There's no n in it. There's no n in it. How many 1/2s do I multiply together?
Oh,
N.
yeah.
N 1/2 multiplied together. Now I have one less 1/2 multiplied together, but I need a full n of them. So what do I need there? Half. A half gives me my one more 1/2, so that I have n of them instead of n minus 1 of them. See?
That's partial. You nailed that.
Now I have n 1/2 multiplied together, and it matches my form of a r to the n minus 1. Follow? So now we can apply what we just learned. What is that sum equal? That sum equals, the sum is a over 1 minus r if r is between 1 and negative 1. Is it? Is r between 1 and negative 1? Yes. So I can apply this. A over 1 minus r. So what is a?
1/2.
What is r?
1/2.
So I get 1/2 over 1 minus 1/2, which equals 1/2 over
1.
1/2 equals, and that's what we said, right? We said add a half, add a fourth, add an eighth, add a 16th, add a 32nd, and eventually the sum of all those would be 1. That's what we said. But now we just use the formula to show the same result, right? This formula that we proved to show the same result. Yeah.
Why is it called geometric? As opposed to arithmetic.
Yeah, so I think geometric is the idea of multiplication. You keep multiplying by another factor on each term.
We have a geometric sequence.
I suppose. I suppose this. Yeah, that sequence would be a geometric sequence. Yeah.
Okay. And so arithmetic sequence is that redundant to say?
I'm not really sure. I don't really know.
Okay. So geometric has to do with the differentiation.
I think so. I think it's referring to the multiplication involved in that. Okay, so try this. Example's messed up here. Go back. That one. Try that. Find the sum if it converges. So first of all, is it geometric? Can we make it be a r to the n minus 1? That's what we're trying to do. Can we get it to be a times r to the n minus 1?
So could we have like 1/5 times 4 over negative 3?
Yeah.
How are you getting 4 over negative 3?
So I'm thinking because negative 3 goes at a higher rate than the 4, it expands at a higher rate than 4.
You said 4 divided by negative 3. How are you getting 4 divided by negative 3?
4 divided. So it's the reciprocal of negative 3 over 4.
Why?
Because first I took out 1 over 5. Took out 1 over 5.
Okay.
And it was just left with negative 3 to the n over 4 to the n minus 1. So I figured that since, since 4 is increasing, no, since negative 3 is increasing at a faster rate than 4, I would have a 1 over 3 cancel out that extra 3 to have it kind of lined up with the 3 over 4.
I'm not following you there.
Okay, so you see negative.
Let's just.
Okay, I guess.
Yeah, you're not going to put negative 3. It's not going to move the denominator. 4 is not going to move to the numerator.
Okay, yeah, scratch that.
Yeah.
So So,
We want to do what we did here. How do we handle this? We have an n here, and we need n minus 1. So what do we do?
We'll have a negative 3.
Yeah, so we can pull out a negative 3, and that'll be then negative 3 to the n minus 1. And then you have 4n minus 1. Is this geometric? Is it a r to the n minus 1? And what is a? Negative 3/5. And what is r? Negative 3/4. Do you see it? Is that what you did?
Yeah.
So we need to get everything at minus 1.
Isn't the first step to try and see if the sequence itself converges to 0?
You could do that, but if you can get it to be geometric and r is between negative 1 and 1, you don't have to do that. You know it converges.
But it still seems like risky because if it doesn't actually take the geometric form, it could just be wasted effort. But if we prove to ourselves that the sequence converges to 0, then we can pursue other methods that we might learn later. Because I'm sure geometric series aren't the only ones that converge.
Right.
But since this is a problem.
Yeah, we're practicing geometric series, right?
Yeah.
So we're practicing geometric series. Okay. Yeah, please.
Would it be fine if I did my parentheses around it with negative 3/4 and put n plus 1 on top of it, like we did? Like, combined it?
And plus 1?
No, n minus 1.
So is it different than this?
Oh, no, it's the same thing. Okay. Like,
Yeah. Is that what you have? Yeah. That's right. Yeah. That'd be okay if you did that. All right, so then equals. So first of all, convergent or not? Because?
It's 0 because I have teachers.
Yeah, because we're going to keep multiplying by 3/4 times 3/4 or negative 3/4, and you're going to get that sequence is going to go to 0, right? That sequence is going to go to 0. All right, and so then it equals
Negative 4/5.
a over 1 minus r, whatever that is. And what's that? 7/4?
Yeah, 7. It's 1 plus 3. There we go.
Oh, brother. Negative 12/35. Okay. Questions? Does that make sense? Last chance. Okay, so then we want to talk about something called the harmonic series. So here's the harmonic series. Is it geometric? Can we write it as a r to the n minus 1? Yes or no? What is the role of n in the geometric series?
It's an exponent.
It's an exponent. It's an exponent.
It's a base.
What about here?
It's a denominator.
It's in the denominator. It's not an exponent, okay? Not geometric. All right, so I want you to write out what this thing is. So write out what is the harmonic series. What does that mean? That should be easy. So when you see that scary symbol there, okay, what do you think? Okay, let's see who hasn't. Yamalix. What does this thing equal? What is it?
Well, the value stands out to be very, very small.
I want to know what this thing means. What is this? What does it mean?
1 plus 1/2
There we go.
plus 1/3 plus 1/4 plus 1/5.
That's it.
So on.
That's what you should have wrote. That's what that is. 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6. On and on and on. Does the sequence converge to 0? The sequence. 1/n does it converge to 0?
Yeah.
Just think of the graph. Just think of the function 1/x, right? 1/x. Does it converge to 0
Yeah.
as x goes to infinity?
Yeah.
Sure. Right.
Aren't
It would-
you adding all those values up?
I asked about the sequence. I asked about the sequence. Okay. Does the sequence converge to 0? Yes or no?
Yes.
Yes. The sequence converges to 0. So therefore, is the sum convergent?
No.
Yeah. Yes.
Does it?
Well, yeah.
Well, according to what you said earlier, yes.
Yeah.
Yeah, it does.
Didn't listen
Is
to
it
that
a
carefully.
possibility or necessary?
Okay.
That's what I'm asking.
All right. So is the fact that the sequence goes to 0, is that sufficient to say that the sum converges?
No, it has to go to 0 quickly.
Okay. So this is all right. It has to go to 0 quickly now. So look at this. So I'm going to compare this to. I want to compare this right here, 1/2 plus 1/3, to 1/2. Pull this here, 1/2. I gotta look at it. So let's, and this is easy. Just don't take all the notes on this. We'll just look at it on Wikipedia. I'll just make it go a lot faster. Okay, so here it is. There it is. 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6. Okay, so this right here, 1/3 plus 1/4, is bigger than 1/4 plus 1/4. Would you agree? 1/3 plus 1/4 is bigger than 1/4 plus 1/4. Okay, so now I'm going to gather these four terms together. 1/5 plus 1/6 plus 1/7 plus 1 plus 8. Would you agree that's bigger than 1/8 plus 1/8 plus 1/8 plus 1/8?
How do we determine how many terms of group?
What works? You do what works.
Just a normal group.
Okay? And then this, so now if I do the next 8 terms, so it would be from 1/9 to 1/16. Would you agree that's bigger than 8 1/16ths added together? And every time I group these together, what is that? How much is that? 1/2. How much is that? 4 1/8.
Oh my god, so it's just forever adding a half.
How many is that? What is that? That's 8 1/16ths.
I say half.
Half. So I can always take twice the number of terms I did before, and the sum of those will be greater than 1/2. Do you see it? So 1/4 plus 1/4 is 1/2. Well, what we actually have is greater than 1/2. 1/8 4 times is 1/2. What we have is actually greater than 1/2. Here's 8 1/16ths added together. What we have in the harmonic series in those eight terms is actually greater than 1/2. So what is happening here? Yeah, all you do is take twice as many terms, and there's an infinite number of terms, you'll never run out of terms, and all you have to do is take twice as many as before, and you'll get a fraction bigger than 1/2. And you keep adding a fraction bigger than 1/2, bigger than 1/2, bigger than 1/2, bigger than 1/2. Take, what would that be? 16 terms will be bigger than 1/2. Take the next 32 terms will be bigger than 1/2. So what about the harmonic series? Convergent or divergent? And it diverged, because you always take double the number of terms before, and you get a number bigger than 1/2, and you keep adding that. You keep adding a number bigger than 1/2. So it diverges. Uh-oh. So I lost my, so the harmonic series over n. So 1 over n, the sequence converges to 0. But the sum diverges. So it's the same thing we saw before with improper integrals. In order for us infinite sum to converge, what must be true? In order for an infinite sum to converge, first of all, what must be true?
So you repeat the question.
For any infinite sum to converge, what must be true?
The sequence must converge.
The sequence must converge to 0.
That doesn't necessarily
But
mean
that is not sufficient. That's not enough. Here's an example where this sequence goes to 0, but the sum is still infinite. The sum is still infinite in size. So what, it needs to go to 0 just like the improper integrals. That sum, that sequence needs to go to 0 fast enough so then as you're adding more terms, the sum levels out, right? The sum levels out to something. Okay, so this is an important theorem here, divergence theorem.
So we're gonna ask again how fast?
It's different. I mean,
It's all good. Never mind.
yeah, that's kind of an impossible question to answer. If you have a certain type of series, you could answer that.
Sure.
But if you're talking about all series, how fast does it need to? I mean, every series is of different structure and form, so you can't really answer that.
Okay.
Within a certain category, you might be able to answer that question.
Sure.
If the limit then what can you say? So given an infinite series, if the sequence does not have a limit of 0, or if the sequence is divergent, then what can you say about the series?
The series must diverge.
He says the series must diverge. Agree? So if the sequence does not approach 0, so it might approach 3 or it might approach -5, or if that sequence is divergent, then what about the sum?
It's convergent.
It's convergent. So then the sum is convergent. The only chance that a sum has to converge is if the sequence goes to 0. And we're saying everything else. The sequence doesn't go to 0, or the sequence is divergent. Therefore, the sum, divergent. Okay? If an so then if the sequence goes to 0, then what about the sum?
Or can.
May or may not. That's right.
Is this the same theorem?
No, this is the Mark-Ashby corollary. because this is the divergence theorem. It's about divergence. Okay? That's about divergence. When does the sum converge? If the sequence does not go to 0, or if the sequence diverges, that's when you get a divergent sum. But if it does, if your limit is 0, then it has a chance, right? You're telling me there's a chance. You're telling me there's a chance.
What is that?
Some people don't know what that is.
Okay.
May or may not. Sorry, that's not or. It's got to get there fast enough. It's got to get to 0. The sequence has to get to 0 fast enough so that the sum doesn't. So eventually, it's like you're adding such a negligible amount that your sum converges. Now, if you have a convergent sum, what can you say about the sequence? If you have a convergent sum,
Then it's also convergence. Then it converges to 0.
it must converge to 0. So if you have a convergent sum, that sequence absolutely must converge to 0. But if you have a sequence that converges to 0, may or may not. May or may not. Okay? Super important. Super important. All right, so let's talk about P-series.
Wait, real quick. What's a theorem?
What's that?
What is a theorem?
What is a theorem? A theorem is a truth. Something that is absolutely factually true based on other things that we assume to be true, or other things that we've proven to be true.
So it is like rooted in other premises.
Of course. I mean, you need to know what one means.
So then
One has to be defined,
yeah.
right? Infinity has to be defined. This symbol has to be defined.
So a theory becomes a theorem once someone's able to.
Yes, right. A theory would be like a speculation. Right. Theorem then it becomes fact, it's truth.
So then what's an axiom?
I think it's like an axiom is like a theorem. It's like a theorem that branches off from another theorem. No, I don't
It's a
know.
corollary, isn't it?
Like a Y.
Okay, but we need to move on.
Okay, let's move on. Good idea.
Okay, so P-series.
Is that NP or NP?
N to the P. How about that? Is that clear? If P is, it's the same as with the improper integrals, right? We had 1 over x to the P. And those integrals converged when P was greater than 1. The sequence converges if that thing is
It's greater.
greater than 0. If the exponent is greater than 0, the sequence converges. But the series to converge, the sum of all of them, P needs to be greater than 1. Okay? So, and this is what we just saw. So the harmonic series is a P series. What's the value of P for the harmonic series? 1, right? And we just saw that that is divergent. As long as you're greater than 1, now for P series, we don't, in this class, we don't look at the sum of it. So geometric series is like the only one where we really actually then find the sum. All the other ones that we're going to do are we're just going to test for convergence or divergence, meaning the sum is finite or the sum is infinite. But we don't find what the sum is. Okay.
What's that? That into the.
Are we clear? Yeah. So that converges, all right? So then there's something called the comparison test. So we got two. So you have two series, okay, with positive terms. Okay, if Bn is convergent and every term of the sequence of An is less than or equal to every term of the sequence of Bn, then what about the series for An? So you have this convergent series, the sequence Bn makes a convergent series, and then you have this other sequence such that all the terms are less than or equal to Bn. And doesn't it make sense that the series An would do what? Yeah.
It's kind of like a squeeze theorem.
Something, yeah. Something like that. A little bit. So then this is not a p-series. But we can use p-series to analyze it. What can we compare that to that we know converges? 1 over n squared plus n is always less than what?
1 over n squared.
He wants 1 over n squared. True statement? So in the one we have, our denominator is always bigger than 1 over n squared. And what about the series 1 over n squared? Convergent?
Yeah, p is greater than 1.
P is greater than 1. So this is a p series with p equal to 2. So this our sum is less than this sum. And this is convergent. Therefore, this one's convergent. This should make sense, right?
Can you explain the importance of positive terms?
What's that?
Can you explain the importance of having positive terms?
Well, yeah, because of the negative terms. So because we want to just talk about less than or equal to. So if you had negative terms that got infinitely big negative, then it would converge. Yeah, okay. So that's kind of goes back to this idea of the squeeze thing. You're kind of squeezing it between 0 and the one you have. That's the positive terms part of it.